Hello, so in this video, I'm going to talk about the Ampere's law, hovering problem, or basically the relationship between magnetic field and electric field and force. So with this, you are going to see a lot of example, like you have this, some object that has an electric circuit, and around this you have a lot of magnetic force, and you'll see the force. So this type of problem, or you see the coiling problem, which is basically you have a lot of coils in which electric current is going through, and as a result the magnetic field is going to be generated. So this type of basically experiment concerning magnetic field, electric current, and force, this is what we are going to talk about in this video. So first of all, when you face a problem like this, all you have to do, first thing you have to do is check if the current is straight or coiled. So what I meant by this is this one. Now this is straight one, and this is coiled one. And when what you deal with straight electric current, you are going to deal with magnetic force and current and actually mechanical force. So this is magnetic force, this is electric current, and this is force. And it's always important to use the Fleming's right hand rule. You always have to use right hand so that you can know the direction. So please see this video. So use your right hand, and it's important not to use left hand. You wanna remember right hand is right, and you wanna remember as FBI, just the government FBI, and F coming from middle finger, it's kind of easier to remember because F and middle finger are nicely planned. So FBI. So when current is going through this direction, and when the magnetic force is directing this direction, the force is basically heading towards you. So this is how you wanna use the Fleming's right hand rule. So yeah, so people remember this as FBI with middle finger F. Middle finger F. XXX. And when you deal with coiled problem, so this is this case, you are only dealing with the two parameter, which is B and F. So in this case you don't deal with the force, so the problem is relatively simpler. And in this case you also want to use the Fleming's right hand rule, but here you want to call it Fleming's right hand grip rule. So the idea is when the current is coiling, you want to use these four fingers as a coil, and you can use thumb as a direction of the generated or generating magnetic force. So for example, when current is going through this way, you want to use this hand as a current direction, so the generating magnetic force is in this direction. So please just practice using by your right hand, since it's important to get used to it. And another things that you have to know when you want to solve this type of problem is typically when you have a straight like case like this, you'll see many hovering problem. So basically the object is hovering, and in this case first equation you have to start with is in the force downward. Usually this is the gravity, and force upward are balanced, which means you can equate force downward and force upward. So this is something you want to know. This is a good tip to solve a problem. And okay, so let's study how let's study the equations to remember. The force applied to the object is F. So this is the straight case, so you only have to deal with FBI, and F equals to I multiplied by L multiplied by B and sine theta. So here L means the length of this object. So length of this object is L. And you wanna put sine theta, but most likely in this case, in this type of hovering case, since I and R are normal, sine theta is going to be sine 90. So normally this is going to be sine 90. So you can write F equal I multiplied by L multiplied by B. Just for simplicity, I think this is most likely what you want to use here. And when coiled, the equation is a little complicated. PL, so again L is this length, equals to mu n L I. So here I is length, and this is constant, what we call permeability number. Permeability constant. And this n is the number of coil, loop. So this is loop number. And I is current. So this seems a little complicated, but basically what you have to remember is this equation and this equation, so that you can solve the problem by yourself. Okay, let's try to solve the problem with the knowledge that you just learned. Okay, please just ignore this one, but let's solve this problem. A current carrying a wire passing through a region of space that has uniform magnetic field of 0.47 Tesla. So here B is 0.47 Tesla, and length is L is 5 meter, and the mass is 3.78 kilogram. Determine the current L needed in the wire, so the wire could levitate. So this is hovering problem. So number one rule to start with when you have a hovering problem is start with F downward equals to F upward. And of course this F downward is gravity. So gravity is m multiplied by g. This is gravity, acceleration of gravity. So 3.78 kilogram multiplied by 9.8 Newton per kilogram. So if you calculate, this is going to be around 37.0 Newton. And now you wanna calculate the F upward. And F upward is obviously this is current carrying through the wire, like without coiling. So this is a straight problem. So what you wanna use is F equal IL B sine theta, this equation. And again, in this case, because I and B are normal, perpendicular, so this can be simplified IL B. Now you know the number of L and you know the number of B, but we don't know the I. That's something we need to obtain in this problem set. And you know the F value, since now this is equal to this value. So this equation can be written as 37.0 equals to I was what does that? I was not known, and L is 5, and multiplied by B is 0.47, right? So I can be written as 37.0 divided by 5 multiplied by 0.47. Then you can get these numbers, 15.67, and unit is Ampere A. So this is how you wanna do. Hope this was useful. See you next time in the video.